Hey guys, what's going on? Back again today. We're going to talk today about speed ratios. Now, keep in mind that basically what we're talking about with the application in agriculture is a spinning shaft. Remember what I said? We can do just about anything with a spinning shaft. My angle set right there. Well, this is kind of a continuation of that. So let's just jump right into it. Read this first part kind of intro verbatim, like I usually do. So, in most machines, the various parts operate at different speeds. For this to happen, speed change must be mechanically accomplished. Generally, speed changes are accomplished via pulley or gears. A multi-speed bicycle is a familiar example. So a 10-speed bicycle has two gears or sprockets on the front, cogs, if you will, at the pedal, and 5 gears or sprockets on the wheel connected to the pedals by a chain. So we have 2 gears up front and 5 gears in the back, and that gives us 10 different gear combinations. The pedal gears turn at the same speed as the pedals, so that's how fast you're turning your feet. But the gears on the drive wheel do not. They turn at a speed in proportion to the gears connected to the pedal gears. So how fast that shaft spins, the rear axle of a bicycle, is a function of how fast your feet are pedaling and what combination of gears on the front and back, what ratio they have. That's how we get the speed of the back wheel from the speed at which you're pedaling the bicycle. Like I said, maybe a little fuzzy right now, but I'll keep going with it. The rider can change the gear combination or change speeds in the common vernacular to adjust the relative ease of turning the pedals and maintain the desired speed of the bicycle. The bicycle example will be revisited again later in the discussions. For the purpose of these calculations, the only significant difference between a gear and a pulley or a cog or a sprocket is that gears, cogs, sprockets have teeth, and a pulley does not. It's a wheel that usually has a little seat in it where a belt or a rope or something like that sits. The pulley has a smooth groove at which the belt rests. In both cases, the primary consideration is the diameter of the device. Therefore, gears and pulleys will be used interchangeably in this discussion. So know the difference. It will make a little bit of difference on some of your calculations, but it's a pretty easy hill to overcome when we get to it. In the case of the bicycle, the speed of the pulley or gear is the exact same as the speed of the shaft in which it is connected. So this isn't really any kind of big groundbreaking revelation here. We have a bicycle wheel and spokes, and this is the tire. If this axle here is spinning at, say, 100 RPMs, well, that means that this tire is turning at 100 RPMs. Like I said, nothing too fancy there. The speed of the wheel, the size of the wheel does not dictate the speed in the way that we're looking at it. It does, and we'll get to that a little later to an extent. But in this case, if that axle is spinning at 100 RPMs, the wheel's spinning at 100 RPMs. If it's turning at 150 RPMs, the wheel's turning at 150 RPMs. If this wheel is 12 inches tall or 100 inches tall, that part doesn't matter. RPMs are RPMs. We've talked about this earlier in the chapter 2, I believe, when we talked about pulleys and simple machines. A lot of the same thing. This axle is turning at the same speed as the wheel. Regardless of their diameters. The difference in speed and torque transmitted to the gears connected to the pedal is a function of the ratio of the connected gear diameters. To determine the proper pulley or gear size, the diameter for an application, both the speed of the drive pulley or the gear and the desired speed of the pulley or gear connected to it must be known. In the diagram below, which I'm looking at, you're not, assume that pulley 1 is the drive or powered pulley and pulley 2 is being driven by the belt connected to pulley 1. Okay, so oh great, forgot my eraser. So let me draw diagram 1 for you. Okay, so in this diagram we have, hope you can see that, yeah. This is pulley 1, this is pulley 2. We're connected by a belt. Now, I'm going to kind of go off script here for a second. But just kind of know, this is bigger than this one, and that means a couple things. The term I like to use is this pulley has more real estate on the outside of it. That means that the circumference is longer. There's more area, more distance around it than on this one. So if we take this and we turn it 1 revolution, and these are connected by chains, we know that that's going to move this belt a certain amount. So this one, pulley 2 being smaller, to cover the same amount of real estate, the same amount of distance in the circumference, it's going to have to turn more than 1 time. So keep that in mind. And that's a ratio that we can, pretty simple ratio that we can calculate. So assuming that the pulley 1 is 10 inches in diameter, so 10 inches, and pulley 2 is 5 inches in diameter, 5 inches, don't slide on me now. And that pulley 1 rotates at 100 RPMs. 100 RPMs. How fast does pulley 2 rotate? Okay, so that's our question. So I'm going to say question mark RPMs. We don't know. That's our variable. As previously stated, the difference in speed is a function of the ratio of the gear diameters. To state this another way, the product of the speed and diameter of a pulley or gear is the exact same as the product of the speed and diameter of the pulley or gear which is connected. So, I've said this, if you're in my class, you've heard this tons and tons and tons, that we're going to use this kind of base formula that generally goes something like this. A force and a measurement, force times a measurement equals a force times a measurement. No, sorry, let me say that again. In this case, let me reword it the right way. A measurement and a force equals a measurement of force. So in this case, we have, I'm going to move my board so I can reach it. D1 times RPM1 equals, let me erase this, D2 times RPM2. Okay. Bring this up here. So what that says, D1 times RPM1 equals D2 times RPM2. Now, what that means, D, pretty simple shorthand, nothing too complicated. D equals diameter. RPM equals RPM, revolutions per minute. So once again, we have a diameter, that's a measurement. We have RPM. In this case, we're going to think of that as being our force. So in that case, it's just pretty simple, pretty basic algebra here. So our equation, we'll call this, side 1 and side 2. So we have D1, which is 10. I can write this a little better. Times 100, which is our RPM, equals diameter 2, which in this case is 5 times RPM2, which we don't know what that is. It's our variable. So I'm going to say RPM2. All right, so we can work this math out pretty straightforward. 100 times 10, 1,000 equals 5 times RPM2. Divide both sides by 5. We end up with 200 equals RPM2. So, in that case, we can jump back over here, and we can say that this question mark, this unknown, is 200. 200 RPMs. So, if for those of you that are watching on Facebook and things like that and YouTube, this may not make a lot of sense to you, but once again, think back to chapter 2. I've said that a lot these last couple of videos. For those in my class, think back to chapter 2 when we talk about simple machines. This is a direct ratio. So if we look at this, this is 10 inches and 100 RPMs. This is 5 inches and 200 RPMs. So this one is twice as big and turns half as fast when connected to this pulley that is half as big and turns twice as fast. It's a 2-to-1 ratio. This is twice as big, so to keep up, this has to turn twice as fast. So once again, think back to that. What I said earlier. So we know if I were to take this blue line and we put a mark right here, and we turn this one complete revolution, that would turn the distance of the circumference. So if this mark, tell you what I'm going to do, put a dot right there and a mark on the belt will travel the distance of the circumference as we turn pulley 1, which is circumference 10 inches times 3.14, 31.4 inches. Now, for this pulley, if we put a dot right there and mark it on the straight up position, 12 o'clock, when this turns, when this belt moves that circumference distance, that 31.4 inches, that means this pulley has to turn that same 31.4 inches. And because it is half the diameter, and therefore half the circumference, it will have to turn twice. So that's how we get this. If this turns 100 revolutions, if we turn this 100 times, this one has to turn 200 times. If we turn this one 100 times in 1 minute, this one has to turn 200 times in 1 minute. And obviously this can be done in any ratio. If this was 10 inches and 4 inches, if this was 10 inches and 0.07123456 inches, we could still, the math works out the same. So pretty straightforward stuff here. Now I do want to change up something, give you a little different example of this. And like I said, very simple change, the same exact formula, just in different wording for a little different application. So let me do some erasing here. Imagine that this diagram, instead of being a nice smooth pulley, was like a bicycle chain. It was a sprocket. So instead of being a round wheel, it has these teeth on it. And once again, sorry for my drawing, but say this has teeth on it. Well, we could measure the pulley wheel. If anybody's ever messed with bicycles or motorcycles, things like that, you know, if it's chain drive, well, you can get out a measuring tape and you can measure the diameter and use this case, or you can do something a little easier. You can count the number of teeth on it. So say this pulley 1 is, we count and it has 44 teeth, and it's the same 100 RPMs. And we count, for the sake of easiness, we count sprocket 2, and it is 22 teeth. Then this is going to be the same 200 RPM. So how we can change this equation a little bit is instead of D1 times RPM1 equals D2 times RPM2, we can change that D for diameter to T for teeth. So T1 times RPM1 equals T2 times RPM2. All right? Same exact equation, nothing has changed. The only difference is we're measuring the number of teeth times and the number of teeth. Instead of teeth of 1 and teeth of 2, instead of diameter 1 and diameter of 2. Because, you know, in a farm application, we think of things where we use something with teeth. So think of a corn planter. You know, there's usually a drive wheel running, you know, the plates that drop the seed. So that'll be run by, that usually has teeth. Fertilized spreaders a lot of times, a mechanically driven fertilized spreader, which is mostly what you see, usually has a high and a low speed setting, and that's usually a big cog and a small, or a big sprocket and a small sprocket on the drive wheel. But that's what we have here. We have teeth. Now, let me just go, you know, kind of like I said, go off script again. This equation, it really doesn't matter how you use it as long as you use like terms. So I can use diameter to diameter. I can use teeth to teeth. I could use radius to radius. I could use circumference to circumference. okay, my math people are going to love this. I could use radians to radians, things like that. So there's several ways you can do it as long as you're using like terms. I can't use diameter of 1, so 10 inches and 22 teeth. I cannot do that. As long as they're like terms, I can do this. Now, one more little quick little illustration I'm going to draw you to kind of go along with this T1 and T2. These are connected by a chain, so think of this as being a bicycle chain. We have teeth, we have chains, there's points. We can count those points as how many teeth we have, but this can also be interlocking gears. So, once again, I apologize so much for my drawing. We have gear 1, and it can be connected to gear 2 without a chain. Interlocking teeth. Now, one thing that will come up on the test, it'll be just for a few points. It's one of those that doesn't really check your math. It doesn't really check your mathematical ability. It just kind of checks for your conceptual understanding. In this case, if pulley 1, sprocket 1, cog 1, whatever you want to call it, is going that direction, means the belt is going this way. That means that sprocket 2 is going in that direction. But in this case, with interlocking teeth, if sprocket 1 is going, gear 1 is going this direction, clockwise, that means it's going this direction. The interlocking gears, the way they work, this changes direction. So gear 2 will be going counterclockwise. So just kind of keep that in mind. I got a little bit of a trick question in there just to kind of make sure you do that, so note that in your test. And I will see you guys later.